Hi guys, welcome back to Ryan Study Corner. Today we are starting our exam prep. Physics exam is right around the corner, so we're going to be working out a past paper week until we get there so that we get as much past paper practice as possible. Today we're jumping into our January 2024 paper 2. We're going from start to finish, so let's jump in. So we have figure 1 shows a copper rod moving through a uniform magnetic field. This symbol, dot with a circle around it, represents the magnetic field coming out of the page. Each end of the rod is connected to leads that are connected to an ammeter, which measures the electric current. The rod is only allowed to move in a horizontal direction, meaning left to right, while in the magnetic field. So we have drawn arrow on the rod to indicate the direction of the induced current. So once we're talking about induced current, we're talking about Fleming's right hand rule. So Fleming's left hand rule is when we have the current and the magnetic field and we're inducing a force. Fleming's right hand rule is when we have the force or movement and the magnetic field and we're going to induce a current. So FBI, force or movement, magnetic field, induced current. So in this case, they ask when it moves to the left. So it means the movement is going this way. They told us that the magnetic field is coming out of the page. So FB, so I want this kind of pointing to me. So let me try and get this good. So FBI, maybe I do it like this. So excuse my weird awkward hand, but everything has to be at right angles to each other. So F, because it's moving to the left, B, because it's coming out of the page toward me, I means that the induced current is going to be acting upward. And we have to draw an arrow to represent that. Then we have name the rule used to determine the direction of the induced current. That's Fleming's left-hand rule. And that's it for that page. So we have an experiment was performed to determine how the strength of the magnetic field affects the value of the induced current. Readings of the speed of movement of the rod and the induced current were obtained and recorded. They're saying given that the rod has a resistance of 25 ohms, use Ohm's law to complete table 1 by calculating the induced EMF. So Ohm's law is V is equal to IR. So if they want us to find the induced EMF, that's V. So we're going to be using I and R. So it means that, let me get my calculator. I is whatever we have here, and we see it's already in amps. So I is 0.0045 in the first instance, and they told us R is 25 ohms. So we have 25. Now 0.0045 by 25 gives me 0.1125. So that's what I'm going to put here. And then I do the same thing for all of the others. Resistance remains the same, so it's going to remain as 25 ohms, but the current is going to change to each one going down in the table. So for the next one, I have 0.0215 as the current times my 25 ohms. Then for the next one, I have 0.03 as the current, and resistance is still 25 ohms. So we have our table filled in. We get 5 marks for that. Pop you. Use the results from table 1 to plot a graph of induced EMF against speed. So once they say this against that, the first one goes on the y-axis. So it means that induced EMF is going on the y and the speed is going on the x. Draw the line of best fit through the point. So keep in mind when we see these 8 marks here, only about half of that is for plotting correctly. The rest is for our salt. Remember, I like to say we like everything with salt. Our graph has to have salt too. Our scale, our label, our axes that are labeled, our line of best fit, and our title. Once we have these things and we plot our graph correctly, we get all the marks. If we only plot the graph perfectly, but we don't have these things, we lose almost half of the marks. So let's go over to the graph paper now. They've already drawn the axes for us. They technically have a title here, but I'll still write in a title because technically that's a figure description. So I'll still put my title to be safe. Now, how do I come up with values? So I'm going to copy this over. And I have to try and come up with a scale now. My x-axis seems pretty easy because they're saying 0.7, so it makes sense that we'll do every 2 centimeters to be 0.1 because that should definitely be able to fit across, and we can check it to see. 1, 2, or I should say 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. So yes, that could fit. So this one here, 2 centimeters represent 0.1 meters per second. Now on our y-axis, we have to go up to 0.95, so practically to 1, and we have to think about what is a good scale. So if I'm counting here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let me give you a hint that my Form 4 physics teacher taught me that I think is helpful, because pretty often we're struggling with a scale. We do something, it doesn't fit, we have to erase and go again. So I know I have to go all the way up to 0.95. Now I have 10 2-centimeter blocks, and we know the standard, we generally do 2-centimeter blocks. So I divide by those 10 2-centimeter blocks so that I can know what is the value I need to put by every 2 centimeters for this 0.95 to fit. So when I put that in my calculator now, I'll get 0.095. Now, we can't use every 2 centimeters is equal to 0.095 because that's weird. It's going to be so much a headache to figure out the values in between. So what I could do instead is say, okay, I know I want like a nice round number that's easy for me to figure out what is the value of all of these small boxes in between. So I want to round this to a nice round number. And the nice round numbers are different variations of 1, 2, and 5. So like 1, 2, 5, or 0.1, 0.2, 0.5. And any kind of variation like that, in the same way, 10, 20, 50. These are nice round numbers that when we divide it by 10 to get the value of each one of these tiny little boxes, it's easy for us to work that out. So looking at it, if I round up, this could be rounded up to 0.1. So I'll say every 2 centimeters is 0.1, and then I can check it to see. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.91. And it fits. So here I'll do 2 centimeters is 0.1 volts. So I have the luxury of being able to zoom in here to put in my values. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. And I know this is my speed axis, so I made sure one time to put U in meters per second. I don't want to lose that mark for labeling. And on the y-axis, it's going to be the same thing. I'll have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and since everything else has one decimal place, I'll put 1.0. And my quantity here is EMF, and I think we used E. Oh no, we used V. So V measured in volts. Now to label, I'll say graph of induced EMF versus speed of movement. You could write out all of that, or if you want to put graph of V against U, since we have actual letters that we're using to represent that. Then I have to come up with my scale. Well, I already came up with my scale, but I have to write it on the graph. So I will say, I'll put it at the side just because I'm not exactly sure how much space I'm going to take up on my graph. So I may come somewhere at the side here and write it, because I don't want that I write it here, which is where I usually write it, and then my graph ends up being like quite up here, and then I'm fighting to see my points through the writing. So scale is on my voltage axis. 2 centimeters represents 0.1 volts. On my velocity axis, 2 centimeters represents 0.1 meters per second. And I'm keeping this here so that I can see my points easily to plot. Now, where do I start? One of the first things I always advise is think about what's the smallest division. What's the value of each tiny box here, so that it's easy for us to calculate and figure out what each one is as we're counting through. So from here to here is going from, remember here is technically 0. So going from 0 to 0.1 is 0.1. And then 0.1 divided by the 10 tiny boxes from going from here to here is 0.01. So it means one tiny box here represents 0.01 meters per second. And then because I use the same scale here, I know that it's going to be exactly the same thing. So from here to here is 0.1. So 0.1 divided by the 10 tiny spaces gives me 0.01. So each tiny box is 0.01. Let me take a sip of water. So I have my first point. U is 0.1 and this is 0.0045. So this is really, really small. If we really think, oh, what am I doing pointing at current? I think this is this. I'm looking for 0.1125. If each tiny box is 0.1, then the smallest I could really find is 0.11. And then 0.1125, we could think about that as kind of between 0.11 and 0.12, but it's practically 0.11. So I look for 0.1, I come up by 0.1, and I know this first line will be 0.11, this next line will be 0.12. So if you want to say, well, if this is the line with 0.11 and this is 0.12, then 0.1125 is going to be in the middle here. But if we think about it again, half of this is 0.005, which means the midpoint there is 0.115, which is actually still a lot bigger than this. So for all intents and purposes, I'm going to plot this at just 0.11. For all intents and purposes, like something fancy. But now I'm doing it in red just because it's easier for me to see and for you all to see. So 0.1 and then 0.11 is going to be right here. Then my next point, I was going to make a little scratch through this because otherwise I'll keep looking at this. Now 0.2 and 0.275, so 0.2, and then if this is 0.2 here, we'll go 0.21, 0.22, 0.23, 0.24, 0.25, 0.26, 0.27. So 0.275 is going to be between 0.7 and 0.8, or 0.07 and 0.08, I should say. So 2 and what was it again? 0.275. So here was 0.25, 0.26, 0.27, 0.275 is in the middle here. Then by 0.4, I have 0.5375. So 0.4. And then 0.51, 0.52, 0.53, 0.54. So 0.5375 is going to be in the middle there. It's really practically by 0.54. I lost my point. Let me find it back. So let me put it practically by 0.54. Then I have by 0.5 and 0.675. .65, and I have a horrible copy here, so I'm fighting for my life to see these lines. 0.5 and 0.675, I think is what I'm plotting. So 0.65, 0.66, 0.67. Works kind of like that. And then after that, I have a reading at 0.6, 0.75, so 0.6, and then I go up to 0.75, which is nice and easy to read off here, because 0.75 is right over here. Oops. That's a little bit off, but we will survive. Now, then I have 0.7 and 0.95. So 0.7 and 0.95 looks like here. So this is my graph. I'm going to try to do my line of best fit, and I can already see I have a little outlier here, unless of course I made a mistake and that's why it's here. But at 0.6 I have 0.75, so that's correct. At 0.5, I have 0.67, yeah. So it looks like it's correct. Hopefully I didn't make a mistake, but I'm horrible at checking over my work. Be better than me. So this kind of looks alright. I might be a off. Um, so now I have everything. So now this is everything for my graph. So once my points are correct and whatnot, I am going to have I'm going to get all of my 8 marks. So now I'm jumping back over here, and they have use the graph to find the gradient g. So I know that to find my gradient, they're calling it g, so I'll put g is going to be y2 minus y1 over x2 minus x1. Now these are two coordinates that excuse me. Excuse me. Now these are two coordinates that we read off from the graph. They can't be points that we plotted already. So I'm jumping back over here, and I'm going to try to zoom in a bit to find 2 points that I could read off easily that I did not plot. So the first one that I'm thinking about is this point over here. I'll put this as my x1, y1, and the x coordinate is 0.15, and the y coordinate is 0.2. Then I'm going to find a point up here. It's going to be pretty hard for me up here just because of the fact that it's not a good copy. So where should I choose? I should probably stick in an area that I could see. So I can see this over here. And it looks like the x coordinate is 0.4, 0.45. It looks like 0.48. Now our points might differ a little bit because of where my line of best fit might be versus yours. And then my y coordinate at that point looks like 0.65. This will be my x2, y2. Now we have to do our little dotted line. One of the marks for gradient is usually for this. It's just dotted lines going from x1, y1 to x2, y2. Right, so let me go and calculate the gradient on the next slide. So my coordinates were 0.15, 0.2, and 0.48, 0.65. So y2 is 0.65, y1 is 0.2, x2 is 0.15, and what am I writing? X2 is 0.48 and x1 is 0.15. So when I put that into my calculator, let's see what I'll get. So I am getting something like 1.36, and on my y-axis I had voltage, and on my x-axis I had meters per second. So technically this is volts per meter per second. And that's my gradient. Now I come over here and they're saying the gradient G is related to the length of the rod L by the equation G is equal to 4.3 L, it looks like. Calculate the length of the rod. So I'll plug my values in first. I got G to be 1.36 and I have 4.3 L. Now if I want to get L all by itself, I need to send this 4.3 over. This 4.3 is being multiplied by L, so when it goes over to the other side, it will switch to the opposite of what it is, which is division. So I will have 1.36 over 4.3 is equal to L. So 1.36 divided by 4.3, I am getting 0.316. Now I am a weirdo who likes to see the letter and then the value, so I will switch it to be L is equal to 0.316, and I'm going to assume that my unit is meters here. Just because my speed, my velocity was meters per second, so it implies that the unit of length that we're using is meters. The experiment shows that increasing the speed of movement can increase the induced EMF. Give one other factor which increases the induced EMF in the rod. So one is use a stronger magnet, You could also do something like use a larger coil, or you could do something like induce, increase the number of turns in the coil. Now we only have to put one, I'm just giving you a few options. Then I have question 2. State the principle of conservation of energy. So principle of conservation of energy tells us that energy is neither created nor destroyed, but changed from one form to another. So that's all I'm going to put here. Energy is neither created or destroyed, but merely converted from one form to another. And define the term momentum stated as SI unit. So the definition of momentum comes literally from the formula. Momentum is m by v. So that's what we're saying. We're saying in words obviously that momentum refers, what did I just spell there? Refers to the product of, or let me say momentum of a body refers to the product, meaning multiplication, of its mass and velocity. Now the unit is, think about it, unit for mass is kilograms, the unit for velocity is meters per second. So the unit is kilogram meter per second. You'd also see Newton second, but when they mention SI units, they're referring to kilogram meter per second. Now, figure 3 shows a girl throwing a shot put in a sporting competition. State the energy changes that take place from the time the girl begins to exert a force on the shot put until the shot put hits the ground and stops moving. So, what am I thinking about her movement here? So, she's holding the shot put here, stationary. Then, when she starts to exert the force, it possesses kinetic energy because it's moving. She pushes it this way, and as soon as it moves from her hand, it's technically potential energy, which then morphs into kinetic energy as it's moving through the air. At the highest point, it has potential energy again, and then kinetic energy increases as it goes back down because it forms this sort of projectile motion here, where if this is horizontal, this is how it's going. So potential energy, kinetic, 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 potential at the highest point, and then kinetic. Then maybe if we say, okay, it makes a noise when it hits the ground, sound energy. So I would probably say that we go from potential energy to kinetic energy as it's moving. Then as it reaches the top point where it would be stationary for like a millisecond, I would say that that is potential energy again. And then it starts to come back down. I would say that that's mainly kinetic energy. And if we want to talk about it hitting the ground, so we see sound energy. because we hear when it drops because a shot put is a pretty heavy thing. So that would be my guess. Now, C says the mass of the shot put is 4 kilograms. I like to highlight or circle or write or whatever so that sometimes when you don't really know what to do, when you see the things that you have and the things that you have to find, it could kind of help us figure out, okay, maybe I should use this equation. So I have the mass, I have the time that she's pushing it for, the speed of the shot put initially and finally, and then calculate the momentum. So I'm going to list everything off here. I have the mass and it's already in SI units, so that's good. I have the time that she's pushing it for, which is 0.6 seconds, already in SI units. Initial velocity is 0 meters per second. Final velocity is 9 meters per second. Now they're asking us what is the momentum of the shot put on leaving the girl's hand. Now it goes from 0 to 9 meters per second, so it's the 9 that we're taking. Now remember, momentum is equal to m by v. My mass is 4, my velocity is 9, so that gives me 36 kilogram meters per second, or you could say 36 Newton seconds, whatever you want to put. What is the acceleration of the shot put? So what are the things that we need to find acceleration? Acceleration is change in velocity over time. So final minus initial velocity over time. Now final velocity is at 9, initial is 0, time is 0.6. If I put that in my calculator, I get, let's see, 9 divided by 0.6 gives me 15, and our unit for acceleration is meters per second squared. Now, what is the average force exerted? So if we just found acceleration and they're asking us to find force, now my mind is automatically thinking F is equal to ma. So force is equal to mass by acceleration, and we know the mass is 4 kilograms and the acceleration is 15, so that gives us 60 newtons. And that's it for question 2. So we're on to our thermal physics question on question 3. Figure 4 shows a car on a sunny day in a Caribbean country. A tourist placed a sunshade inside the windscreen to reduce the temperature rise of the air inside the car. Which material, dull black, dull white, shiny black, shiny white, is most suitable? Now, shiny reflects best, and then white absorbs the least. And we want all of the light to be reflected, we want very little to be absorbed. So I'm going to go with the shiny white. So shiny white is the most appropriate, or most suitable is the weighted they use, since shiny materials reflect light. And white is a poor absorber of radiation. And complete the scenarios below by inserting the word which best describes the main process of thermal energy transfer. So it's either going to be conduction, convection, or radiation. A girl goes for a walk on a coulee. She touches an iron gate that removes thermal energy from her hand. This energy is then transferred through the iron gate by what? So once there's physical contact, it's conduction. The girl holds the sides of a cup containing a hot drink. Her hands gain thermal energy by, now, they intentionally set this up this way. They use a hot drink because they know once we hear hot fluid, we're automatically thinking convection. But technically, she's physically touching the hot material here, so it's actually still conduction. Convection is why certain parts of the cup or certain parts of the fluid will be hotter, and why the fluid will move in a certain way, and why certain parts of the fluid will be less dense than the other. But here she's in physical contact. The hot tea is touching the cup, making it hot, and then the cup is touching her hand, making it hot. So it's conduction. Now, some farm workers light a fire. Once we see fire, radiation, heat. The girl warms her hands by the side of the fire. Her hands gain thermal energy by radiation. Now, define the term specific latent heat of fusion. Now, anytime we see the word specific, it means per unit mass, as in per kilogram. Anytime we see latent, latent means hidden. Now, fusion means melting. So to define this, I'll say this is the amount of heat energy. Let me write that a little less scrappleful. The amount of heat energy required to melt 1 kilogram of a substance without a temperature change. So 1 kilogram is because it's specific. Excuse me. We have to say without a temperature change because this shows that it's latent. If we do not say that, we'll probably just get 2 marks rather than the 3. Then we have small pieces of ice with a temperature of 0 degrees Celsius are added to 0.35 kilograms of water. The initial temperature is this. The water loses this much energy as the temperature of the water decreases to this. Calculate the specific heat capacity of water. Now, I have let me list my stuff. My mass is 0.35 kilograms. The initial temperature is 24.5 degrees Celsius. The final temperature is 0 degrees Celsius. And the water is losing this amount of energy. So what is the specific heat capacity? So E is equal to mc delta T or mc delta theta. We already have the energy. They told us the water loses 35,000 joules. And they told us that the mass of the water is 0.35 kilograms. We don't know what C is. And then the change in temperature is going to be 24.5 minus 0. Now, this does not need to be converted to Kelvin because we're looking at the change in temperature, meaning the amount of units that we're changing through, and not necessarily about the unit of temperature. So let's say moving from 8 degrees Celsius to 10 degrees Celsius is the same as moving um, from 273 Kelvin to 275 Kelvin. It's the same temperature change when we look at it. So this could simplify to 35,000 is equal to 0.35 by C, and anything take away 0 is itself. Now on this side, I'll simplify things a little bit. I'll put 0.35 by 24.5. So 35,000 is equal to 8.575 by C. Now algebra again, I want to get C by itself. Only thing preventing it from being by itself is that 8 point something. So I'll send that over. Right now it's being multiplied by C, so I'll switch to division when it goes over. And I'll have 35,000 divided by 8.575. And that gives me 4081.63. This is specific heat capacity. So we're talking about joules per kilogram per Kelvin. Now you could put joules per kilogram per degree Celsius. That's fine. Anyone here, they would generally give you the mark for. So now our next part says find the mass of ice added to the water if all of the ice melts. So what we have to think about is that the heat that the water lost in cooling is the same heat that the ice gained to melt. So I'll say that the loss of heat energy from the water is equal to the gain in heat energy of the ice. So it means that same 35,000 joules is the energy. But remember, since the ice is melting, it's a phase change, so we use ml. So the energy is 35,000. We don't know what the mass is. They told us here now that L is 3.3 by 10 to the 5. Now, to get mass all by itself, I'll send this over to the side. It's involving multiplication, so we'll switch to division. And we'll have 35,000 over 3.3 by 10 to the 5. So then my mass is 35,000 divided by 3.3 by 10 to the 5, which gives me 0.106 kilograms of ice. So now we are on question 4. Visible light, radio waves, X-rays, infrared, gamma radiation, and UV radiation are types of electromagnetic waves. Name the electromagnetic waves in each of the regions labeled A, B, C, D in the electromagnetic spectrum shown in figure 5. So they made it a little bit trickier here. They're trying to trick us a little bit. Because usually we go from left to right. We start with the largest wavelength here, which is radio waves, and then we work our way down to gamma rays. They intentionally turned it the other way. So it means we're starting with radio waves, then we have microwaves, infrared radiation, visible light, UV radiation, and then X-rays, and finally gamma radiation. So A is X-rays, B is UV radiation. C is infrared radiation. And D is microwaves. Now state which sound wave parameters affect each of the following properties. So pitch is not a physical quantity, pitch is just a sensation we feel as a result of a high frequency of the sound wave, and loudness is just because the sound wave has a high amplitude. Now we're over here. A person standing 100 meters from a wall claps his hands and hears an echo 0.6 seconds later. So the wall is here. I'm standing over here, I clap my hands. Now I'm standing 100 meters away from the wall. So for the sound wave to reach to the wall, it travels 100 meters. Now for me to hear the echo, it means that the sound wave has to hit the wall and bounce back, so it comes back this way. So really it traveled 100 meters to the wall and then 100 meters back to my ears. So it takes 0.6 seconds for me to hear that. So it takes 0.6 seconds for that sound from the clap to come here and come back over here. So what is the speed? Now, speed is equal to distance divided by time. But remember, the distance here was 100 meters to go plus 100 meters to come back. Or we could say 2 by 100. And my time is 0.6. So if I put that in my calculator, 200 divided by 0.6, I get 333.33 meters per second, which we could kind of round off to 333 if you like, because that's 333 and a third. I'll just leave it like that. You know, the speed of sound is roughly like 330. Now, Figure 6 shows a plane mirror AB. A ray of light strikes the mirror at point X with an angle, so at X is here, with an angle of incidence I between 0 and 90 degrees. So let me get my ruler so that I could draw it looking halfway decent. So it means this looks like it's at right angles here. So this is my normal. And we want to complete the path of the incident ray and show the reflected ray. Mark on the diagram the angle of incidence and the angle of reflection. So my ray is coming in this way, and then it's going to be perfectly reflected this way. This is I, this is R, but still I'm going to make sure to label these because we don't want to lose marks for not labeling. So this is my incident ray. This is my reflected ray. This is my angle of incidence. This is my angle of reflection. And that's it. We're good to go. Make sure to draw your arrows here because in questions like these, all of these things factor in for marks. Now question 5. Differentiate between alternating current and direct current. So DC current has a set value while alternating current oscillates or has an oscillating value, its value changes. So direct current has a constant value while alternating current you could say has a changing, or we can say oscillating because it kind of goes back and forth. It's not like it's just changing randomly. And then we could also say that direct current flows in one direction while alternating current flows in both directions. Or maybe I want to say flow while alternating current alternates directions. Or switches. I don't really want to use the word alternate when we're describing something that has alternate in the name. So while alternating current, let's say continuously changes direction. Now, a transformer is a device used for stepping up or stepping down AC voltages. Draw the electrical symbol of a transformer. So my drawing is going to be horrible, just keep that in mind. Mine always looks kind of like fingers, or maybe like toes, I don't know. But something essentially that looks like this. This is representative of the primary coil, secondary coil. State two advantages of using alternating current rather than DC. So alternating current can be transmitted at high voltages and low current, while DC can't. AC can be the voltage and an AC supply can be easily adjusted. And for all of these, my undertone is while DC can't. So DC can't have a high voltage and a low current to transmit. DC, the voltage can't be changed as easily as AC. AC as well can be used in transformers because we need a changing magnetic field, which is caused by the AC supply, and that is what induces the current on the other side. If we had a DC supply, because there's no changing magnetic field as a result of it, because there's no change in the DC supply, we wouldn't be able to step it down or step it up afterwards. So any one of those things could work. Now complete the statement below. Transformers work on the principle of mutual induction, like we're inducing the current and inducing the EMF. A mobile phone charger contains a step-down transformer which converts the input of 220 volts to a working output voltage of 5 volts. If the output current that flows into the mobile phone is 120 milliamps, calculate the input current from the AC supply. So I like to kind of sketch the transformer. It's a step-down transformer. This is our supply, and then this is what we're getting. The input side, our primary voltage is 220 volts, while my secondary voltage is 5 volts. They're telling me that the output, which would be my secondary current, is 120 milliamps. So I'm going to convert that to amps one time. Milli means by 10 to the negative 3 or 1000. So calculate the input current from the AC supply. So I'm trying to find IP. So my formula is my standard formula is primary voltage over secondary voltage is equal to number of turns in primary over number of turns in a secondary is equal to current is always the opposite. So now I'm going to just use V and I. Now it doesn't matter. We could flip all of these and have them in the opposite direction. Or, top and the bottom. So I have VP over VS is equal to IS over IP. And when I plug values in, it means 220 over 5 is equal to 120 by 10 to the negative 3 over IP. And I'm going to cross multiply, so I'll have 220 by IP is equal to this by this. So then I want to get IP by itself, so I'll take my 220 and send it over. It's involving multiplication, so we'll switch to division. So I'll have IP is equal to 120 by 10 to the negative 3 by 5 over 220. Now when I put that into my calculator, I get current of 0.00273 amps. Now I'm just leaving it in amps. We could also convert it to milliamps or express it in standard form. I'm taking the lazy way out. But I mean, it's still correct. They didn't explicitly ask us to express it in any other way. So now they're asking us to determine the power supplied by the secondary turns of power. Now power supplied is usually given as P is equal to IV. And since they mentioned on the secondary side, we need the secondary current, which is 120 by 10 to the negative 3, and the secondary voltage, which is 5. So 120 by 10 to the negative 3 times 5. I think I just did some craziness. Gives me 0.6 watts. Then they're saying if there was a 10% loss of power within the transformer, calculate the actual power delivered to the secondary circuit. So if you want, you could say, let me find 10% of that 0.6 watts and then minus it. But I'll think of it as if we're losing 10%, it means the only amount that we're actually using for useful output is 90%, which is the remainder after that 10% loss. So I'm going to say, well, what is 90% of 0.6? So that will tell me how much was actually used. So the actual power is equal to 90% of 0.6, which gives me okay guys, so I didn't realize that my mic died, so I'm going to do a voiceover for the last part, question 6. We have the cloud chamber is a device used to detect the 3 types of radioactive emissions, alpha, beta, and gamma. Figure 7 shows a cross-section of 3 identical cloud chambers containing the different sources. Now, alpha particles are strongly ionizing, beta particles are weaker ionizers, and then gamma are just horrible ionizers. So the gamma radiation tracks are going to be thick, bold lines. Beta is going to be a little bit weaker, not as thick and bold. And then gamma radiation is going to be really, really thin and weak because it can't ionize well, so it almost looks like tadpoles. Now we have state 3 properties of gamma emission. So this is just anything that we use in describing gamma emissions or gamma radiation. So first I have gamma radiation has no charge. And I have gamma radiation has no mass. And then finally, gamma radiation is an electromagnetic wave. So now we're on to part B. We have figure 8 shows the graph of the mass of a radioactive isotope against time elapsed. So we have mass on the y-axis, time on the x-axis. This is really a graph that allows us to find the half-life. Now, the first thing they ask us to find is the initial amount. And if I look between 1200 and 1400, then that's a difference of 200. And then if I look at the amount of spaces, now initially I mindlessly put 10 because I'm thinking it's a graph. And then I realize, okay, no, let me count it. And in counting, I realize, hey, it's actually 5 spaces between there. So I have 200 divided by my 5 spaces. That tells me that one tiny space here is 40 grams. And this looks like 2 boxes above, so 1200 plus 1 block is 1240 plus another block is 1280. So the initial mass is 1280 grams. Looking at the time it takes for the amount that we have to decrease to half the original amount. So this graph now, we'll start with particular values and then look at the amount of time it took for that to drop to half of that, and then take another value, look at the time it took to drop to half of that. Starting with 1200, because I could look at the difference in going from 1200 to 600 because both of them can be easily read off from the graph. So I go across with a dotted line until it touches the curve, and then I go down to read off the respective time value on the x-axis. Now that looks like 2. Now I'll go by 600, go across with a dotted line until it touches the graph, and then go down to read off and see what's going on my time axis. And when I read that off, that looks a little bit like 16. So the half-life here would be the time it took to go from 2 seconds to 16 seconds, 2 hours to 14 hours. What am I saying? 2 hours to 16 hours, and that's 14 hours. but they ask for the average half-life, so I'm going to use a couple more values. So now I'm going to look at the time it takes to go from 800 to 400. So I go across at 800, touch the line, and then go down. That looks a little bit like 10. My line is a little bit off. But then when I go now to 400, that looks like 24. So that's 14 hours going from 10 to 24. Now we could stop here and just use 2 intervals, or we could use 3 intervals if we want. So I'm going to look at the time to go from 400 to 200. So 400 we already had 24 hours, so that was our endpoint. Now this kind of looks a little bit like 37.5. Now again, I can't really tell for sure because of the quality of this, but we could work with that. Now that means that we don't end up with 14 hours here, we end up with 13.5, but then that's fine. That's the purpose of doing the average. If you got 14, that's wonderful. I got 13.5. So now I'm going to find the actual average. So the first value was 14, then my next value was 14, and my third value was 13 and a half. So I have 3 values there, so I'm going to divide that by 3. When I put that in my calculator, I get, oops, I forgot to divide it by 3. So I got 13.83 hours as my half-life. Now for the very last part, I have the half-life of another radioactive nuclide is 10 hours. Determine the fraction of this radioactive nuclide that remains after 30 hours. So first I'm going to say if 10 hours is one half-life and we have 30 hours, then 30 divided by 10 leaves 3 half-lives. So I have to count 3 half-life intervals. Now I start up with like 1 or the whole. I go through a 10-hour, which is a half-life interval, and I'll be left with half of the original amount. Half of 1 is 1/2. Now I go through another half-life interval, so I end up with half of the amount I had before, which is 1/2. So half of 1/2 gives me 1/4. Now I have another half-life interval where I'm having half of the previous amount, which is 1/4, and that gives us 1/8. So this means that the fraction that we have remaining is actually 1/8 of the original amount. And that is it, guys. So next week we're working on June 2023 paper. We're going from beginning to end. I will make sure everything is charged so we can have a seamless session, a seamless video. And that's it. I hope this was helpful. Bye.